Okay, Assalamualaikum and good morning. Today we're gonna continue with our lectures. I hope your test is okay. So let me just recap what we did. Again, I don't have typed notes at the moment. I'm still typing the old ones. So let me recap what we are doing at the moment. Just looking at chain rule, some complicated applications of chain rule, and we had this example. So we're not going to do the example again, but I'm just going to write down what it is so that you can remember from the previous lecture, and then I will continue from the results. You had this application of all this substitution of variables rather than replacement of variables, and then you're supposed to find some partial derivative. Okay, so let me just write it down first. So you are given all these things, and then you are asked find the UDS and the UDT. And when I say the, I mean the partial. Okay. So what was done is to look at differentials of each of these equations. So I'm not going to write those down, but essentially once you have the differentials, and then so in other words here you will have du in terms of dx, dy, dy and dz. Okay, so that's the differential of the first equation, but then dx will be written in terms of ds dt, and similarly for dy and dz. Okay, so in the end what you're going to get is you'll be able to express du in terms of ds and dt. Okay, so once you have that, then one can start finding your partial u, partial s, and partial u, partial t by remembering that the u can be expressed as partial u, partial s ds, and then partial u, partial t dt. Okay, so that was what we did previously. So today what we're going to do is to have a shorthand notation. Let me see. I hope that's done. Okay. To have a shorthand notation of what's going on. So let me just push this up. Okay. So one could give so one could sort of compactify your notations of derivatives. Partial derivatives. As if they are matrices, okay, in terms of matrices. So this would be a convenient way to write things down. So let me just write it. So what you have is essentially your u is, remember your u is a function of x, y, z, okay, but you are required to find partial u, partial s, partial u, partial t, okay. So I can think of this pair of partial derivatives as a matrix. So this is a matrix 1 by 2, and so this is what you do not know, so this is not known. And how do you get this is by taking what is known. So in this case, what is known for u is your partial u, partial x, partial u, partial y, partial u, partial z. So this is a 1 by 3 matrix. Okay, so there's a triplet component thing. And how to express to this 1 by 2 partial derivative matrix is to multiply it with, okay, so you probably can guess it has to be compatible. So the matrix that you have here should be 1 by 2 should be obtained from 1 by 3 times a matrix 3 by 2. Okay, so what is the matrix over here? Well, it's just remember that your x, y, and z are going to be functions of, so your x, y, and z, I'm not going to write everything down, will be functions of s and t, and similarly for y and z. So what you can do is to have another matrix of partial derivative that gives you the x, y, and z derivative with respect to s and t. And when you multiply the matrix altogether, then really what you have is something like a chain rule. Okay, so that's the main thing. So it's a convenient notation, and sometimes, sorry for the ugly looking matrix. So what is convenient about this is you can even compactify this further into an equation which is a symbolic equation. So you can put as a symbolic equation just to remember what you're doing. So you have a function of concern which is u in a bracket. Okay, so this is not really a partial derivative. So the bracket just tells us, okay, what is the function, what are the variables. Okay, so here you have your bracket s and t. Okay, so this is representing this matrix. I hope you can see the cursor. Somebody? Pretty quiet today. Can you see my cursor moving? Please say yes or no. Oh, you can see. Okay. So this part, so let me just put a different color here. So this part is symbolically represented by this. Okay. So your u is your function, and your s and t is your variable. Okay. And then this will be equals as the symbolic equation. Again, what are the functions? The function is u. And what are the variables in this particular case? It's x, y, and z. Okay. And what about this? What are the functions? The functions are x, y, and z. So you have x, y, and z. And what are the variables? The variables are s and t. So in a way, you can sort of see this as like a, a generalization of a chain rule. Okay? There's a bit of a cautionary note. This notation should not be confused with some other thing that you have learned. Okay, or maybe I should indicate. So this is that, and this is that. Okay. Just a caution. We have another thing that appears in maths, which is the well, which looks like this, but it's not the no, the derivatives as you see it over here. Okay, we have also what is known as Jacobian, which has more or less the same kind of notation. For example, partial u and v, partial x and y. This just tells us how to convert, and essentially this is a determinant. Okay, so let me just write it down. Oops. Oh, this is v. This one. Okay. So this is different. Okay, this is different. So you have to understand the context. When a Jacobian, it means a determinant. So you're not doing per se, but you have to take no, the determinant of that matrix. So just to make a cautionary note over there. Okay. Now, you might ask, why are we doing all these things? Probably, let me just mention one other example from the book. I'm not going to do all. So, it's important note over here. So what we have done so far essentially is to look at, maybe I just summarize first. Summary over here. What we did was to use differentials to get partial derivatives. Okay? This is a very convenient technique, particularly in physics, because sometimes you have functions expressed in many different variables, and one needs to make some kind of partial derivative of them with respect to these different sets of variables. So these are a common thing to do in physics. So you need to be able to know how to get the partial derivatives, and this can be done through differentials. Now, the idea here is this is, you could have taken, for example, variables u and v, the other way around, sorry. You could have taken the variables x and y, for example, and replace it by u and v. The problem with this kind of replacement here, why not? So maybe why not replacements? Okay. The problem with that is sometimes you have cases, examples where you cannot really express them in a nice set of equations. So here is going to be an example where you can really do that. Okay, so let me just write the example over here. So the answer over here is essentially there's these cases where you can write the relations directly. So doing differentials give you a way of overcoming this problem. Okay, so let me just write down the example now. So the example here is the first example from the book. Okay, you are given this kind of equation. So you can see is now in terms of quadratic equation over here. And then another one equation in terms of a trigonometric relation with an exponential. And then the other one could be something very simple. And the question here is, what is partial z, partial t? Okay. So if one looks at it, no, there's no way you can actually solve x in terms of t and y's in terms of t directly. Okay, because the equations are quite well, it's non-linear in a way. So you won't be able to do easy replacement kind of solution kind of thing. So what do we do? So we take the differential between all these three sets of equation. Let me just see. I'm looking at the right thing here. So let's do the first one. Okay, take differentials. I need to push this up a little bit because I'm running out of space on my tab. Take differentials. For example, the first equation will have 2x dx plus 2y dy, and then it equals to, my handwriting is getting horrible, 2t. Yes, I remember that I could not write very fast, and once it's delayed a little bit. So and let's do the other one, the other equation. So the other equation is this one. Yeah, since you cannot see the cursor. So that would have sine t dx, and then you need to take the differential of sine t, so that will give me x cos t dt. And then on the other side of the equation is so everything in terms of y here, so I would have ey plus yey dy. So let's simplify this first, okay, so that I don't get confused myself. So let's simplify this. So I can, no, the factor of 2 is a common factor there, so I can remove that. So I have x dx plus y dy equals to t dt. Now on the second equation over here, I will try to make it your dt onto the other side of the equation. So I would actually have sine t dx bit confused. Oh yeah, okay. Plus, oh, it's a minus, sorry, because we're bringing this one to the other side. Okay, so that would be a minus. So I would actually have minus 1 y plus 1 e to the y dy, and then I bring the dt on the other side, and that gives me minus x cos t dt. Now, again, what do we have here? Well, you can think of this as a matrix. So this is what I have something dx dy here, and then this is what the matrix multiplying here is x and y, and then I have sine t minus y plus 1 e to the y, and then this gives you t minus x cos t dt. So you have seen this type of equation before. You want to solve, say, a variable here, okay, in terms of a given, well, I could have put dt inside here, okay, dt is a common thing. A variable here, solve in terms of some given expression over here. So what can you do is to use the Cramer's rule. So this is going to be a bit complicated, so it's not my type of way of looking at things, but of course one could actually do it. Solve for the x and dy. So what do you do? For example, the x will be given by determinant. So in order to have a solution for dx, okay, you replace this column. So let me just write it down because you cannot see the cursor over here. So I will have to replace this by t dt minus x cos t dt, and then I replace the, well, I mean, I keep this other column, y minus y plus 1 e to the y divided by the determinant of that 2 by 2 matrix, x sine t y minus y plus 1 e to the y. And of course you can try to solve this. I'm not going to know. So you get something in terms of dt. Okay, so you can look at the same thing applies for dy. Again, you just simply replace the second column now. So here is x sine t. So the second column is replaced by dt dt minus x cos t dt, and then divided by the same column. So it's pretty messy. Okay, that's why I never like this kind of things. But again, no, a lot of realistic what you call problems tend to have complicated expressions, and by using this Cramer's rule, you are able to actually write the expression down. But today, we have computers to actually help us to do that. So what's okay? we go back to the equation, the question itself. What is the problem? The problem is to find the z dt. Okay. So, but the z, where is it? Oh, I haven't done the differential of that. Okay, let me just write it down over here. So we'll have again some expression in terms of dt. So your z equals to x minus y. Okay, so that will give you dz equals to dx minus dy. Okay, but now you have already an expression for dx. Suppose that you have actually solved this. Okay, then this will give, let me write this as, say, capital A, and this is capital B. Then I will have capital A dt minus capital B. Okay, and from that you can you are able to find out what your partial z, partial t is. Okay, in fact, in this particular case, you can simplify this. Of course, no, there will be no other things appearing inside here. Okay, so you can now find the z dt in that sense. Okay, for the other, there are, I think, other two examples in the book. You may want to have a look at it and try to understand it. Okay, but the next thing that I want to do is to look at again partial derivatives in a way sometimes you have to be very careful about how should I say, thinking in terms of the derivatives. You might need to know what functions actually are involved. So let me clear this. So the example that we're looking at is a coordinate transformation. I have another half an hour left. So of course, let's do the simple one, which is your xy coordinate turn into a what you call polar coordinates, which is r and theta. So this is x in terms of r and theta, y in terms of r and theta, but you can also re-express r in terms of x and y, which now is a bit little bit ugly in a way, and here is essentially you have inverse tangent of y over x. Okay, so again, one could ask the question, what is, say, how do you get d theta dx, for example? Okay, so let's do that. So here I'm going to rewrite the original equation of this. So I'm going to put tangent theta equals to y over x. So if I do a differential of this equation, or I could even differentiate it straight away. Secant squared theta is the derivative of tangent theta with respect to, say, with respect to theta. Okay, but remember what we want to do is taking this derivative. Okay, so you have the secant squared theta d theta dx, and then on the right hand side you also differentiate with respect to x. That gives you minus y on x squared, and essentially you can now rearrange this to get your d theta dx, and this is 1 on secant squared theta times minus y on x squared, what is secant squared? That is simply cos squared theta. And then over here I can write your x squared at the bottom as r squared cos squared theta, so that in the end you sort of remove the cos squared theta there, so you get minus y over r squared. Okay, which is okay. I suppose you know how to do this, hopefully. So now what we want to do is to make the comparison between dx d theta. But this is simpler because x is given as r cos theta, so dx d theta is essentially r minus r, minus r sine theta. But what is r sine theta? R sine theta is y. And you can see now, okay, this is not quite, so what I want to say here, you'll find it that your, okay, I've been being very clumsy here. I should have taken all as a partial derivative, sorry. So forgive me for that. So over here, what happens over here is one can actually immediately see partial theta partial x is not equals to partial x partial theta inverse. So why is this? Okay. Well, no, sometimes you have seen the way that we do calculus as if, okay, if we take the derivative of a function f, or say a partial derivative of y with respect to, say, x, and then you want to find partial derivative of x with respect to y. Sometimes what we do is just to make some what you call simplistic what you call assumption that you can actually do the reciprocal. So here the point of this example is to show that you can't really do this all the time, because you have to remember what are actually kept constant and what are actually not kept constant. Okay, so what happens over here is that the thing that you should have kept constant, if you want to make them to be reciprocal, whatever is kept constant over here should be also kept constant over here. Okay, so this is the thing that we want to do. So if one keep constant, for example, y, okay, so here essentially what we did in this particular equation over here, let me just oops, no, not that. I want to bring the screen a little bit down, so let's mark this a little bit. So what we did in this particular set of equation, when we take the derivative with respect to x, okay, this is trying to get d theta dx, okay, partial theta partial x, sorry. When we do this differentiation, we are keeping y constant. So that's the reason why I'm putting a y over here, to say that I'm keeping y constant. Okay, and then you get this expression. So if I really want to be consistent, I would need to have this expression. Let me just go back to black. I would also need to find out partial x, partial theta with y kept constant. Okay, here, let me put it in a different color here. Here, what is kept constant over here? The one that being kept constant is r. So it's not y being kept constant. Okay, so we need to be able to do in a way how to find this partial derivative with y to be kept constant. Okay. So what we do is to re-express your x in terms of y and theta. So let's recall what we have over here. X equals to r, what was it, cos theta, y equals to r sine theta. So if I want to replace your r, because you want to keep y constant, so I need to put r to be y over sine theta. Okay, so in other words, if I want to do this derivative, I have to re-express your x as function of y and theta. So that will give me what? So that will give me y over sine theta times cos theta, which is equals to y cotangent theta. I'm running out of space. Right, so now let's try to do this. Okay, so if we take partial derivative of x with respect to theta, but now we're keeping y constant here, so you get essentially this would be what? What's the derivative of cotangent theta? Well, if you do not know, you have to go back to first principle and find out, but I'm going to just write it down. This is going to be minus cosecant squared theta. And what is cosecant squared? That is essentially y over sine squared theta, which is equal to minus y over, so if I use this again, this equation again, I'm not seeing it again, let me just put it down a little bit. Okay, so then I will have sine theta equals to y over r. Okay, so that would give me y squared over r squared. What does that give you? That will give me minus r squared over y, okay, which we can now compare with the one before with d theta dx. So let me put this in color here. Okay. No, I don't want to complete that. Okay, so you can see this is minus y over r squared, and the dx d theta that we have just calculated is minus r squared over y. So here, by making sure what are the variables that kept constant, we are able to reproduce this equation back, which is partial theta partial x equals to, so kept constant y partial x partial theta kept constant y, and take the reciprocal. Okay, so one has to be aware of all these problems with respect to what is actually kept constant. Okay, so that no, it in a way that tells us no, your partial derivative is a bit more no, you have to be a bit more careful in trying to do the derivatives. I'm going to skip this, I think. There's a part where you can rewrite your equation again in terms of matrices. So I will skip that. You can have a read. That's on the section after this particular explanation. So let me go on to the next thing that I want to do. By the way, can we have our replacement class on Friday? Maybe you can discuss this in the WhatsApp group, okay? So that if you are all okay with Friday this week, then we can have a replacement class then, and like the one we had planned before the unexpected break, okay? Okay, so let me probably just clear the canvas. Okay, the next thing that we want to do is essentially in the, using partial derivative, okay, using partial derivative to solve what we call the maximum and minimum problem. Okay, so let us recall some of the basic things that we have done in ordinary calculus. For example, when you write y equals to f of x, recall, okay, then one can find the maximum or minimum, okay, by taking the derivative and set it to be equal to 0. So what you get is essentially, if you try to solve this, basically you get what we call the stationary points. This is much more general, okay, which could be a maximum or minimum, or it's a saddle point. Okay, I think you have done this, I think even in high school, so I do not need to. So this corresponds to something like this, and this corresponds to something like that, and then this corresponds to something like that. Okay, so again, we want to generalize this in a much more general setting. So remember how we do this is to look at single variable function to a multiple variable function. So in this case, let's consider this one, for example. So we can think of this as a surface. Okay, so what would be the equivalent problem over here? Okay, again, on the surface, one could have something like that. No, one could have something, a surface of this nature, which is like a hill, or valley, or it can be a saddle point, which I do not want to draw it because I'm not good. So I'm just going to cut and paste this. Snapshot. Oops. So here's a saddle point. This is a surface again, and you still have that kind of the analogous thing that happens in in two-dimensional space, but in one-dimensional curve. But now it's in sort of turned into a surface, okay, in 3D. Okay, so again, what would be the conditions that we want to take? So the conditions that we want to take is similar to the one given for the ordinary case. Okay, you take the derivative and equate it to be equal to 0, but over here, so the thing that you need is something like the z dx equals 0, as well as the z dy equals 0. Okay, so let us do an example. Hopefully I can finish this in time. Here's an example. We want to build a 10 of some volume V, okay, and the 10 doesn't have any floor, no floor, so you just have something like this. Actually, there's a diagram in the book, but I'm not going to paste again. So theta here, theta. So this is an what you call isosceles triangle here, and then this is 2W over here, and this is L. Okay. So what the problem wants to do is to minimize the way it's being phrased inside the book is minimize the material to build up the 10. So what would that correspond to? Okay, the material will actually have been covering this part of the area here, an area at the back, okay, area here, and an area on the left hand side and the right hand side. Okay. So and there's no floor, so the floor doesn't count. So the equivalent problem that we want to do here is to minimize the area. I'm running out of time now. So let's just write down the expression of the area and the volume. So let's do the volume first. Okay. The volume V is given by what? The base. Okay, the base times length times height. Okay. So what is the base over here? The base consists of this isosceles triangle, for which you can actually have to find out what is the height here. Okay, so let's draw it. So here I need to know what is this height, right? Given that this is W. So you can do ordinary trigonometric thing. You know that tangent theta is actually what h over w. So in other words, h is going to be w tangent theta. Okay, so then that will give me only a half of that. So I'm going to put everything down now. So the base will be, let's say, half times 2w times okay, that's a bit, sorry, I was confused with the height now. Okay, the length is times L, and then the height is what we have just worked out just now, it's W tangent. Okay, so let's simplify that. That gives you W squared L tangent theta. Okay, so to work out the area, so you have to work out this area and this area, okay, and no, it's being repeated twice there. So I'm just going to write things down now without too much explanation. So area of the case of the triangular shape should be given by this half w tangent theta times 2, okay, because I have these two isosceles triangle, well, two right angle triangle to build up the isosceles triangle, and then I need to multiply another 2 because I have the one at the front and the one at the back. Okay, so that is the triangular shape, and then I need to find the one with the rectangular shape. The rectangular shape, you have to find what is the length here. Let's say this is the length d, so I need to find what d is. So this is theta here, this is w, so and I know cos theta will be w over d, so d will be w on cos theta. Okay, so again, so I need to add this up, so I will have plus w over cos theta times L, okay, and then remember there is the left and right triangle, sorry, not triangles, rectangles, so you have to multiply by 2. So let me simplify the whole thing. And again, we already have v equals to w squared L tangent theta, so I can replace one of them. I think probably let me write things. So L over here, I can re-express it in terms of what? V over w squared tangent theta. Okay, so I'm going to replace that everything here, and then simplify everything so that I give you the answer in the end. 2w squared tangent theta plus 2v on w cosecant theta. Okay, so this is the thing that we need to minimize. Can we finish it? Okay, maybe let's just finish it. So what do? We take the derivative. Okay, so what are the variables here? The variables are going to be your w, okay, variable, and then your theta. V is kept fixed, remember, V is given by that. Okay, so what we need is essentially to have partial A, partial W to be equal to 0, and partial A, partial theta equals 0. Okay. So the first one, just solve this immediately. So the first one is partial A, partial W, that gives you 4W tangent theta minus 2V cosecant theta over W squared. Oh dear, never mind. W squared equals 0. So that's that. Okay. And then we do the other one, which is 2W squared secant squared theta minus 2V on W cosecant theta cotangent theta. So you have to remember how to differentiate cosecant theta here. Otherwise you do it by first principle again. And that gives you this equation. So since I'm running out of time, probably we want to continue with this in the next lecture. Okay. So the next lecture, can we discuss this if possible this particular Friday, 3 p.m. onwards, because this is the time that we have discussed before. Okay. So I hope you agree to this. So if there's any problem, just let me know on the WhatsApp. Okay. So I will stop here now. I have another meeting after this. Stop here now. So let me take the attendance. So, okay, that's probably it for today. And we discussed the replacement lecture on WhatsApp. Okay. Okay, thank you everyone. All right.